Hello and welcome to another finite element analysis lecture. In this lecture, we are going to discuss impact analysis with FEA. I'm going to introduce two different integration schemes that are used in impact analysis. One is explicit, another one is implicit. We will choose the explicit solver and integration scheme to describe how we can run an impact analysis.
By the end of this lecture, you will be able to describe the advantages and disadvantages of the explicit integration, explain the concept of the stable time step, recommend methods for improving the explicit simulation runtime, explain why the hourglass energy should be monitored, and predict the impact response of structures using the explicit solver. So why do we need to know about this? Many design problems and challenges involve mechanical loading at high rates. An example is designed for crashworthiness in road traffic collisions. In fact, road traffic collisions are the fifth cause of disability-adjusted life years lost among all diseases and injuries globally. They also kill 1.35 million people each year, with 50 million surviving after sustaining injuries. So impacts are rare and catastrophic events. Finite element modeling is often the only method for understanding their effects and designing optimum systems to protect against these effects. Here I've shown an FE simulation of a bicycle head collision. We know from biomechanics research that head rotation can shear brain tissue and cause injuries, such as diffuse axonal injuries. At the Head Lab at Imperial College, we design and test new technologies that can reduce head rotation during impacts. What you can see here is the simulation of a bicycle helmet, and we show that in 10 milliseconds how much the head has been rotated.
I explained before that when a system is under loading, often, all the time, loads vary with time. Sometimes we can ignore the inertial effects of the loading, and these are called the quasi-static problems, but sometimes we cannot ignore them, and these are dynamic problems. When we want to solve dynamic problems, you remember that we came up with equation of motion in FE terminology. That equation, just to remind you, was this matrix, which is the matrix of nodal masses times the vector of nodal accelerations plus matrix of damping, vector of nodal velocities plus structure stiffness matrix, vector of nodal displacements equals all the external forces that are applied to our nodes. So this is our equation of motion in FE terminology. When we want to solve this problem, you can imagine this is a dynamic problem. So loading is happening in a certain time. Imagine, like in impact analysis, we are often looking at something around 100 millisecond or less. If it was blast, probably it was even less than a millisecond. So we are looking at different time scales, but what matters here is that the variables, like the field variable, which is for us is the vector of nodal displacement, it changes with time. In order to solve this problem, we need to take a stepwise approach. That means that we need to break down our time domain into smaller steps. So if our time for the simulation, we are concerned about first 100 milliseconds of the loading, then we would break that 100 millisecond into smaller chunks, like 1 millisecond or 100 nanosecond. we call that steps, or those steps, we call them delta t, the increment in time. So we start from time 0. So imagine if at time 0, time itself is 0, so we start with value 0 for time. Then we are really concerned about finding the vector of nodal displacements at any follow-up time points. So here is a generic time point which I'm showing with n, and this corresponds to a time that is n times delta t. So n times the number of time steps that we have taken. So you can see we have broken our time, imagine 100 milliseconds for an impact, into smaller chunks, and now we are going through these smaller time steps step by step and solving our equations. So if I consider that as the time where we are concerned about our unknown, then I can write that equation of motion for that time, which would be this d, but this is at time n. Right, so this is the vector of nodal accelerations at time n, which is n delta t. This is vector of nodal velocities at time n, and this is vector of nodal displacements again at time n, equals, again as I mentioned, forces can change with time, so external forces, when they change with time. For this equation, we are concerned about time t, which is n times delta t, so this is Rn. So this would be our equation of motion.
The explicit algorithm uses the response at previous time steps to determine d n plus 1. So here you can see that dn plus 1 is a function of acceleration, velocity, and displacement at previous time steps. This algorithm can easily deal with non-linearities, which are 3 types in structural mechanics: contact, geometric, and material. To be stable, the time step has to be smaller than a value called the critical time step. It is suitable for blast and impact analysis. So essentially problems where the time, the duration of the phenomenon is comparable to the wave propagation time throughout the medium. The implicit algorithm, on the other hand, uses the response at previous time steps plus acceleration and velocity vectors at the current time step to determine d n plus 1. So here you can see the values at the response at previous time steps and acceleration and velocity at the current time step. So this algorithm does not have the stability issue, so the time step can be large. Each time step, however, involves calculation, which involve many more manipulations and requires substantially more storage space. This approach is suitable for dynamic problems that are significantly slower than impact problems. A widely used integration scheme used for explicit simulations is the central difference integration scheme. First, we can estimate acceleration at time n from the equation of equilibrium. So you can see I've rearranged the equation of equilibrium to find the acceleration at time n. Then the vector of nodal displacement at time n plus 1 can be found as shown here. So here is the central difference scheme, and from that we can work out the vector of nodal displacements at time dn plus 1. And here's the vector of nodal velocities at time n, which can then be evaluated from this equation. A key parameter here is delta t. So the question is that what should be the size of delta t? Can it be anything, or there is some limits on it? In reality, the size of delta t depends on the minimum length of elements and speed of sound in our material. How?
Speed of sound is the speed at which sound travels within a medium. So imagine this rod here. If I hit one end of the rod, there is a wave, there is a stress wave or strain wave that travels along the length of this rod, reaches the end and reflects back. So really the speed of sound or speed of dilatational wave in our rod is the speed at which this initial wave that I'm creating travels throughout this rod. You know, in air, speed of sound is around 300 meters per second. But when it comes like to metals, as we look here, speed of sound is much higher. So sound travels much faster in metal media. In a nearly one-dimensional structure like this rod, this is nearly one-dimensional structure, we can find the speed of sound or the speed of this dilatational, so-called dilatational wave by using Young's modulus and density of the material. So speed of sound in this nearly one-dimensional structure is square root of elastic modulus divided by density of the material. Well, a question. This material, this rod, is made of aluminium. Do you think if it was made of steel, the speed of sound would have been higher or lower? Well, we can calculate the values and look at that difference by using this equation. So if I consider two materials here, one is aluminium and another one is steel. Elastic modulus in gigapascals. In aluminium is around 70 gigapascals. In steel is around 200. Density in kilogram per cubic meters. For aluminium is around 2,300, and for steel that's 7,800 roughly. And now we can work out the speed of sound, which is c, and that would be in terms of meters per second. If you do that, if you insert this into that equation and find the speed of sound, you will see that in aluminium the value would be 5,516, and in steel that would be 5,063 meters per second. Interesting, no? So you see speed of sound in aluminium is higher, slightly higher than in steel. Well, what is the importance of this in explicit solvers? We will see that in a second. In explicit solvers, the stable time step should be smaller than the time required for sound to travel across the smallest element in our finite element model. So the time step should be smaller than the time required for the wave to travel across the smallest finite element in our model. So what do I mean? Imagine if we had this rod and we want to develop a finite element model of this rod, and let's say we want to simulate that kind of impact that sends a wave across our rod. If I mesh this rod by using solid elements, and I'm just focusing on central region, one region in this rod, so I'm just exaggerating that. Imagine this is the rod, and these are the solid elements that we have used. Well, of course, the aspect ratios are not great here, so we try to make the aspect ratio better if possible, but that's not the point. The point here is that if we send a wave through our finite element model, the wave front at time t, well, I'm starting from this end. If the wave front at time t is here, this is time t, and then at time t plus delta t, the wave front is here. If you use an explicit solver and delta t is this large, this simulation will fail. Why? because the delta t is too large for the element to realize that there was a wave, a dilatational wave that arrived at the element and passed through the element. If you imagine these are two snapshots in time, at time t this element does not see any wave, and at time t plus delta t this element, this one, does not see any wave either. So time has elapsed and this element has not seen the wave passing through it, and this will cause the solver to fail. Instead, this delta t should be small enough so that when this wave is traveling through the finite element model, so here we have time t, this element now is able to see the wave, yes? So delta t is now short enough for that element to see that there was a wave that was going through. So, of course, I'm describing it in a more descriptive way. I'm explaining this, but there are also equations to use for this. The equation that we often have is delta t, which is the stable time step. It has to be smaller than L over C minimum. So L is the characteristic length of our elements, and C is the speed of sound. You can have different materials in different parts of your model, and you can have different size elements in different parts of your model. That is fine, but you can then work out the ratio between L and C, which is that time we are talking about, that's delta t, and you find the minimum value of this, and this delta t, this has to be smaller than L over C, the minimum value of the L over C. This ensures that there isn't any single element in our finite element model that is not able to see the wave traveling through it. Well, I mentioned that C for a nearly one-dimensional structure is square root of Young's modulus over density. If we have a three-dimensional structure, then C is a bit more complicated. So it would be the square root of K, bulk modulus, plus 4 over 3 G, which is the shear modulus, and this is divided by the density of the material. Well, in reality, when you start your simulation, your impact simulation, you may realize that this delta t, the stable time step, is too small. Roughly from my own experience, impact analysis of protective equipment, brain models, etc., I see that like composite materials as well, this delta t is often something around like 50 nanoseconds all the way up to like 700 nanoseconds. But we also can end up with values of delta t that is really small. Imagine if this delta t that we're expecting to be something around 100 nanosecond then becomes 1 nanosecond. That means there will be 100 more loops that our software has to go through in order to solve this problem, because the time domain is now divided by hundreds more time steps. So there are ways to make sure that this does not happen, or at least you sanity check your model and, if possible, improve the stable time step, which means we try to increase and maximize this as much as possible. One of the reasons that this delta t can be very small is small elements. So here we would appreciate that this L plays a very significant role in reducing this limit for delta t. If that L is very small, then that delta t has to be small. And it is also possible that there is only a single element in your entire model. You may have a model of hundreds of thousands of solid elements, but there is only one tiny element that is too small, and that tiny element is governing the entire simulation for you and ruining the entire simulation. In other words, it makes your simulation 100 times slower in order to complete. In those situations, you should look for those very small elements. I have an example here. You see all these elements are relatively large, but when it comes to this element here, you see this one is very small, and this element is going to govern our delta t. So it's going to make our delta t extremely small, and it will affect the entire simulation. These sort of elements are often created because of the constraints we have on the CAD. For instance, if in the CAD model of this body, we had lines here, then we are imposing having a node on the line when you are creating the mesh. Obviously, it depends on the application, but it may not be necessary at all to have such a tiny element. Hence, you can go and toggle, you can remove those edges and make sure that the mesh generator is not constrained by those lines. So it doesn't have to put an element across those two lines and therefore creating such small elements. So you can look for across your mesh and try to remove those small elements by removing the geometrical constraints and remeshing your structure. So that's method number one. Another method is to see if the structure that is governing this delta T, if that is really important to be included in the stress analysis. Sometimes we have complex parts. One part of this entire system might not have much deformation. Stress propagation in that part may not be important. You may not be even concerned about the fracture of that part, or it may not fracture at all. So there might be an opportunity to make that part rigid. If you make it rigid, of course theoretically rigid, then the software will not include that part into the calculation of this bound for the delta T. A third way to go about increasing this stable time step is to look at C. You know, C is a function of density. So you can artificially increase the density of those elements that are governing this delta T in order to increase this entire L over C value. This approach is called mass scaling, but of course you should be very careful because you are artificially increasing density and therefore you are influencing the inertial response of the finite element model. So you should be very careful if increasing the density in those certain locations, it will influence the response and affect the quantity of interest or not.
I mentioned that the explicit integration is good for dealing with nonlinearities. Now it is important actually to look at these nonlinearities very briefly. We have three types of nonlinearities in structural mechanics: material, contact, and geometric. And as I mentioned, the explicit algorithm can easily deal with these nonlinearities thanks to the very small time increments imposed by the limitation on the stable time step. So material nonlinearity refers to the behavior of the material. It happens when stress is a nonlinear function of strain, depends on the loading history, etc. Two examples are nonlinear elasticity and plasticity. Here we can see a linear elastic model that I have shown here. So this is a linear elastic material where the slope is independent from strain. So you see when we increase the strain, this slope remains the same. However, here you can see the behavior of a nonlinear material where you can see the slope of the stress-strain curve depends on a strain. And mathematically we can show this relationship like this, where E, if you remember, is the material model or constitutive model, where here this is independent from strain, and in this situation it depends on a strain. Contact is a nonlinear problem in nature. It deals with situations where a gap between adjacent parts open or close. The contact area between parts changes as the force changes or the contacting surfaces slide on each other. All these situations should be predicted in small increments. For instance, here the contact algorithm checks if the node of surface 1, which is usually called the slave surface, has penetrated into an element of surface 2, which is usually called the master surface. In step 2, it detects penetration, as you can see here. So one of the contact methods, which is called the penalty method, it puts a string at the location of penetration to push back the penetrating node, as can be seen here. The stiffness of this spring is calculated by the algorithm, but you may be able to increase it if you still observe significant penetration during contact. And finally, geometric nonlinearity refers to situations when the deformation is so large that the stiffness matrix must be updated using the deformed geometry, not the initial geometry. Here you can see a plastic fork under lateral loading. When the deformation is small, the element stiffness matrix, more specifically matrix B within the integral of the element stiffness matrix, which is the derivative of the shape function, can be determined using the position of the nodes in the reference or initial geometry. However, when the deformation is large, like in this case, the current position of the nodes must be used to calculate matrix B. And this is what we call the geometric nonlinearity. And then making predictions here again needs this stepwise incremental approach, which again, thanks to the very small time step, the explicit algorithm is usually very good in dealing with this sort of nonlinearity.
I hope you recall from our discussion of solid elements that the element stiffness matrix is found by evaluating this volumetric integral, so integral over the volume of the element, and this includes this matrix B, which is the spatial derivative of shape functions, and E, which is our constitutive model or material model. I explained there that one of the schemes we use to evaluate or approximate this numerically is the Gauss scheme. In Gauss' scheme, we are using certain points within the volume to evaluate this function and then multiply it by the weights and add them all up in order to approximate the integral. So if we focus on a linear hexahedral element, let's say this hexahedral element, which is linear, it's made of 8 nodes. Yeah. We can use 8 Gauss points in order to integrate this one. So we can have 2 points in each direction. So let's say 1, 2, 3, 4, and then some below, in the plane below, so here, there, and there, and there. So all of them are within the volume of the element across different axes. So we have 8 integration points. If we use 8 integration points for a linear hexahedral element, we call this a full integration. But this can lead to some challenges, like when your material is nearly incompressible, like in brain, or most elastomers that we are dealing with. Then using full integration may lead to some instability problems, or it may lead to over stiffness of our finite element model. So a remedy for that is to use a single integration point. So what I mean is that instead of using those 8 integration points, we can evaluate that integral by using a single integration point, which of course is located at the center of our hexahedral element. So instead of 8 integration points, we can use a single integration point. This means that computationally this is much faster than that one. We just evaluated that in 1 point than 8 integration points. And then we can also eliminate those problems with like nearly incompressible materials, instability, and over stiffness. But there will be a challenge. So the big challenge of using single integration scheme is that our model may produce the so-called spurious deformation modes or the hourglass modes. So these are deformation modes that do not require any energy, or they do not have any resistance to deformation. So what do they mean? First of all, with the single integration, we can, the model, the finite element, can sense deformations like this. So you can see this is like stretching our element, right? So we are stretching our element, or shearing of our element. So it could be this mode. Yeah. So if we have this sort of deformation, single integration can feel it, can understand it. So this is the so-called non-zero energy deformation. But there are other deformations that this single integration point does not have any resistance to. So they would look like this. So if we have a deformation like this, so you see this edge is extending and that edge is contracting, that central point does not feel that deformation. It can be the other way around. So it can be like this edge. So the vertical edges, this one is extending and this one is contracting. And again, if you use a single integration scheme, then this does not really feel these kind of deformations. We call them the zero energy deformation. So what happens as a result of that, you could have a part of your structure where the shape of the elements, if you look at a number of elements, they would look like this. So you have an element that is deforming like that. You see this edge is contracting, that edge is extending, this edge is contracting, that edge is extending, and so on. So here we would have like this. Okay, so you see now we have 6 elements, and then they have had this zero energy deformation, and you can see the shape of these two central elements. This looks like an hourglass. That is why this zero energy deformation is called also the hourglass deformation or hourglass mode. In order to remedy this, the approach is to apply forces in these nodes in order to resist against this zero energy deformation. But you can imagine the forces that we are introducing, these are numerical forces, so these are not physical forces. As a result, there will be some energy that is produced within our simulation that is caused just by our numerical manipulation of the model. This energy is called the hourglass energy. And we should always monitor the hourglass energy inside our model in order to make sure that it is small enough. A rule of thumb is that the hourglass energy should be less than 10% of the internal energy inside our structure.
Great. Now let's solve an impact problem using the explicit algorithm. So the problem you're looking at here is a spine protector. Spine protectors are embedded inside garments that motorcyclists usually wear in order to protect their spine in case there was a fall from the motorcycle and the contact with the ground, with vehicle, etc. So spine protectors must pass the EN 16212 impact attenuation test. I have explained the test here. In this test, a 5 kilogram mass is dropped on the spine protector at a 4.472 meters per second speed. So in fact, what is defined in the standard is the energy, which is 50 joules impact energy. And I have worked out the speed from the mass of the impactor. The impact force measured at the anvil base, which I've shown here, must be less than 18 kilonewton if this is a level 1 protector, or 9 kilonewton if it is a level 2 protector. So my question here is that, does a 2 centimeter thick block of Agilis pass this standard? So this is a very crude approach to this problem. What I have put here is just one layer of Agilis, which is a viscoelastic material, and we have characterized this material previously, and I just want to roughly check if I have a block of Agilis, would it pass this standard or not. So in order to define Agilis, it's a visco-hyperelastic material. So you need to have some properties for it, which we have actually characterized in our previous publications shown here and used it even in one application. So you need to use the density, the incompressibility parameter. So this parameter is usually defined within the hyperelastic material model. So I recommend for this problem, make it simple, and we use the Newhookian material model. It's one type of hyperelastic material model with an initial shear modulus of 162 megapascals. So actually Agilis is quite viscoelastic, and its shear modulus at very high rates is quite high. For the viscoelastic definition, use this table to define the coefficients of the shear relaxation modulus at 3 characteristic times. So essentially this shows how much this initial shear modulus is reduced at different times. So I have solved this problem in a supplementary video which I invite you to watch. So in summary, in this lecture, we learned about the advantages and disadvantages of the explicit integration. We learned about the concept of the stable time step. We learned some methods for improving the explicit simulation runtime, in other words, increasing the stable time step. And finally, we learned about the hourglass deformation modes and energy and the rule of thumb in terms of this artificial energy generated by hourglass deformations. I hope you have enjoyed this lecture. Thank you.